All right. So let's start, by writing something. Right. So this is the basic thing that we are looking into. So yeah, so let me recap a few things here right now. Yeah. So I would put a few lines, something like this. So this is a second lecture to the introductory series of mathematical physics. And in the series of mathematical physics, we are currently looking at the vector analysis. So all aspects of the vector that we are very much concerned about, for example, the aspects of vector, especially the way physicists look at it, right? That's what we are interested in. So what we will be interested in, something like I said to you, we are interested in particularly vector algebra. Of course, not in a very detailed fashion, not in a very detailed manner. You see, because somehow I assume that a basic operations of vector algebra, and because you are a grad students right now, so we will be very much willing to teach you something like differential calculus with vectors. And then, of course, we will move to integral calculus. I think those two are the very important aspects of vectors, particularly right now, what we are discussing. So yeah, and in the recap, so these are, of course, they are running things, right? We have not completed, they are in running. I mean, of course, I have not even touched this part, right? So allow me to say a few things. Yeah. Okay, I think those syllabus things we will sort it out and let you know in a while. Yeah, so right now the thing is we are just focusing on our class, and let's look at this. So in a recap, I would also mention a few things. So what we have studied so far, right? So we know that how do you define vector? So definition wise, you are very clear, right? What you mean by vectors. And so we have also seen that, right? How you measure vectors, right? So that was very important for us to know how you measure something like, let's say, a position vector in a XY plane. So it was very important for us to know that, right? How you measure it. That's what the very essence, right? That's the way you, and all definition turns out to be there, right? Because you see, this is a quantity which, any quantity which is represented by a arrow here, it happens to be a step in a three-dimensional space. Let's say third axis is somewhere here. So you have seen, right, that basically the way this step is defined, it is very much I mean, we have seen a few operations, like if I say number A, so that was your basically translational operations. And number B, I would say that was basically your rotational operations. Right? So rotational operations. And we have seen very peculiarity about it, right? So can someone summarize to me, I mean, for in a line, what were the summary of these things? Anyone? Any students? I think I just want you to speak about it, because I think that would be nice to know whether you are on the same page or not, right? So yeah, anyone is listening or everything is okay? Because I'm not getting.
Sir.
Yeah.
Sir, can you repeat what you said, sir?
Yeah, sure. So what I said, basically, what we are trying to look at, the basically the definition of vector. We are defining it. Define a vector. That was the motto. And while defining it, we know that how we are interested to measure the vectors, right? And then at the same time, we are very much interested to do a few I mean, we want to play with it by saying that, for example, I have a coordinate system with something like origin, and I want to measure things from here, right? So now someone asks you a question and say that, what is special about it? Why you are willing to measure something from here, right? And then someone says that, no, take my origin somewhere which is sitting here, right? And then you define whatever you said here, and the define same thing here, and write down the laws for me, whatever you are interested in to study, whatever physics or anything, right? So that's what we have looked into detail, right? And what we said too about it, we said those are basically associated with the translational properties, right? We have also seen what will happen if you just, now you rotate it. I mean, the axis will no longer be something like this and this, but it will be something like this and this, right? So these are, again, let's say, make it exact. So these are again solid lines, but denoted by 2 arrows. So now if I rotate my axis something like this, what will happen to my laws? So this was your homework, right? I'm very much willing to know whether you have completed or not, or any problem. So the homework was basically write down Newton's laws in this frame. So I wish you have completed those things. And if not, you can also ask me sometime whenever we discuss things or things like that, because the homework part, I would prefer that unless you specifically don't ask me, I won't put my extra time on that. And of course, when we are discussing our assignments and things like that, we will look those aspects too. I mean, I will first discuss homework things, but I would prefer to you to take initiative and try to complete those things. Okay, fine. So let me again remind you a few things that I defined to you, the differential calculus. So with this, basically, now since allow me to take a few things here. Yeah. So what I want to say now, coming to the algebra, I mentioned a few things to you, right? Suppose, for example, if A is a vector, right? You know how to combine two vectors, right? These are the basic aspects of algebra. Now, you can also know that how to multiply two vectors. And what this multiplication seems to be, this is something like a scalar quantity, right? A scalar, right? And then you can also multiply something like this, right? And this turns out to be a vector, right? So these things, you know, what are the basic algebra associated with the vectors, right? So this is, I would say, basically, these are the aspects of algebra associated with vectors, A, B, whatever you number them, and you can find out, right? Now let's look at the other aspect. Like I said, we will be interested in mostly in calculus, right? And you will see why that's so, because in physics, you're very much interested in solving the differential equations, isn't it, right? The entire physics exercise is nothing but to write down few set of equations and try to solve it, right? That's all the physics basically focuses on. But the point is, you see, the beauty, the way physics and mathematics are defined, you will also notice that the mathematical tools are very essential for physical problems, especially to study physics, isn't it? But somehow in physics, we try to look at once we write down the equations, for example, for a particular problem at hand, even solving a fundamental mechanical problem associated with Newton's equations of motions, right? Once you have set up your problem, what the aspects, you will see that even the equation itself is a differential equation, isn't it? In physics, I mean, that's the beauty of it. I mean, all things boil down to writing some sort of differential equation, and finally the conclusion is can be drawn by solving those set of equations. But there comes a very important aspect, the way physicists look at solutions of a given differential equation and the way mathematicians solve it. You see, in physics, basically, people try to I mean, look at the nature of solutions specifically rather than exactly solving it. That's the beauty of physics. And you see, you can very much know about nature by even just looking at the nature of solutions. Even that is not my quote. I would maybe say who quoted it is basically the famous physicist or mathematicians, P.A.M. Dirac, right? Who is one of the founding father of quantum mechanics. So who basically says something like this. So that's the beauty of your physics. You want to solve it, but you don't actually solve it, but try to figure out the nature of solutions. Whatever the solutions, you can figure out maybe asymptotes or maybe all limits, you try to figure it out and then look at it how, I mean, nature can behave in that fashion. But what mathematicians does, they have some different aspects to look on the problems. And so they basically, you see, there's a famous debate, and the debate is something like when mathematicians come to a physicist class, and he always comments like, you guys only solve just a first or second order linear differential. I mean, when even the mathematicians will look at electrodynamics, he will only comment to you that you have a certain set of differential equations, I mean, first order or maximum second order or whatsoever. So, and then that's all you have, right? But you see, physicist says that's all we need, because we don't need more than that. So entire thing is contained over there. So that's the beauty of physics. You see, you will notice as you will go along. So yeah, but today's class is basically, we look at some tools which is very essential for your to study physics, isn't it? Because physics is a you see, I mean, I'm getting more philosophical here, but I somehow feel that that's also very essential when we discuss any subject, especially a subject of kind physics, right? Because the core, the physics spirit somewhere lies in its philosophy, not in its mathematics. I mean, various people look at it in various angles. I would not say that that's the fundamental, very fundamental approach, but that's the way it is. I mean, in physics, people look at the basically the way spirit of subject is, and that's come through the basically not through mathematics, but through more like rigorous arguments or trying to something look philosophical aspects of it. But anyway, let me stop here. So let's look at basically the differential calculus of vectors. So when we formulate differential calculus, I said to you basically the one operation that I want to write to you before you, that I define a set of x's, let's say x and y axis, where I said basically I have temperature contours, right? And these temperature contours are defined, let's say 30 degrees Celsius and 20 degrees Celsius. And then I said, let's measure a point P who has a coordinate somewhere x, y, z, if this is my z axis. And let's say I have a point somewhere here, let's say P prime, and let's not say P prime, because you see we are using prime for rotated systems, so that would create some confusion. So let's say P1, some point P1, which has a coordinate x plus delta x and y plus delta y and z plus delta z, right? So that's the way. And when I said basically, I just want to write a full change in this vector, right? In this vector, let's say whatever you want to say. I mean, let's say basically what exactly happened to your basically your even temperature gradient moving from one point to another, right? That was the basic question. And once I said I derived before you that what exactly it will look like. So the full change of any quantity, how this will look like, right? So the full change of any quantity will look like something like gradient of that operator multiplied by that vector, isn't it? So that was the basic idea of writing a full change. And once you do that, you will notice a few things. And the few things were something like this, that this operator, what I call basically a gradient operator on some function, and this function, this is a vector thing, right? And you see this field, this temperature field is a scalar field. This is a scalar field. And I introduced to you by what you mean by scalar field, right? A field which is defined on the each point of space-time, let's say defined here, here, everywhere, by defined through these temperature contours, right? So the field which is defined on each point of space-time, but you don't need direction to specify it. You just need a number to specify it. That's what it means. But you see this grad, what I said, basically grad, this grad is basically, that's your vector operator, right? And basically this full change can be written in terms of this grad t, and then of course basically operate of basically a vector, right? Something like this. So this was the total result that we have formulated, right? And this grad t basically is what this is now, right? This is what? A vector, right? A vector quantity. A vector quantity. Okay, all right. So that's what, and what when it is a vector quantity, it has some component, right? And what are those components? It can be something like this, right? They constitute these three components, right? So yeah, so let's look at a few things now. Now you see, I also specified to you that in normal, for example, in a linear algebra, I'm not very sure if you are familiar with it, but let's look at it. So if I say, if I have a vector A and I want to multiply it with a scalar, let's say what that scalar is, I will say, you see, I'm just taking T as a scalar here right now because that defines my temperature contours, right? So I would say basically you can combine these two things something like this way, right? Or you can combine something like this way, isn't it? Are you following me? Anyone would reply to me?
Yes, sir.
Yes, okay. So what I said basically, now whether these two things will be equal or not, can someone say something about that? If this is a is a vector and T is a scalar, so will these two things will be equal or they won't be equal? Yeah, I'm just
Equal,
waiting.
sir.
Equal, okay. So yeah, I mean, that's right, because that's what linear algebra says. I mean, if you multiply a vector with a scalar, I mean, either you multiply from right or left, it should not matter, right? So yeah, so now what my point was, you know, we are now dealing with some operators, right? And this is my grad operator, what I said basically, it is a differential operator. Okay. It is a differential operator that will operate on some function. And you see, this is an operator and this works over here. So why not we can write something like this? Is this true? Can you comment? Someone can comment on that?
Sir, this is not equal.
Yeah. Yeah. So you see, so why that is the case, that you will see in a while. We have seen that these things cannot be equal because of the fact, you see, the way this operator operates on this, that means this, when this operator operates on this scalar, it generates a vector function, isn't it? So that means this is an operator which is very much like, you can say, it's very eager to differentiate something, right? That's what it is called, a differential operator. And this is eager to differentiate, right? That's what it is for, eager to differentiate. But what about this thing? This thing, I mean, is still an operator. I mean, it's still an operator which requires to be operated, right? Because here you see this operator has operated and it has performed his function, but it is no longer hungry here, right? Because it has been feeded what it needs to be feeded. It needs to be feeded some function. Right now, we are talking about a scalar function. So we feed it a scalar function, and this operator has operated over here and generated a vector function, isn't it? So the operator has been satisfied. But in this case, this operator is still a hungry operator. It requires something to be operated. So these two things will not at all be very much like the way linear algebra works, isn't it? So so the way basically you see that's why the operator algebra is a bit tricky. So that's a bit cautious right now for you, caution. So you will see that the forms of this operator algebra very much frequently. You will see this in basically your quantum mechanics. So you will see in a while as you go forward. So the operator algebra is very, I mean, we should really careful be dealing with those sort of things. So now let me summarize a few things. So I think I have done this in the previous class. So I would say let's write here. So, and then in addition to all those things, I have written a thing called, even you see, when I say something like this, you can also see a notation, something like this. If I want to write delta f in book somewhere, you will see also df, I mean, the way this full function is changing. So the change in this function f between two consecutive point can be written as this also. In some books, I mean, some prefer this, some prefer this. So it's just a matter of notation. So I said basically the way you write delta f, you can always write this as something like if it is a function of x, y, and z. So del f by del x, delta x, del f by del y, delta y, and del f by del z, delta z, right? And I said basically this relation will hold true when these approaches to very infinitesimal, like in the limit particularly, these things will go to 0. So these are the parts of your.
Sorry to interrupt, Rohit, but
Yeah.
in general, delta people use for the difference, like a finite difference, you have f1 minus f2 or something like that.
Mm-hmm.
But for infinitesimal change, generally people use it like a df. So probably if you use the same notation, then that will be the, nice. Right.
Yeah, I mean, it's not it's just a matter of fact. I mean, I prefer
like a consistency.
Yeah, true. So it's okay. I mean, I am okay with anything, whatever you feel, because you will see that basically those who, I mean, in the electromagnetism, when you see basically when you will follow, you will find, I mean, people prefer writing something like this. So it's okay. You can choose one of these things. So, and one thing I would also say to you that basically when I write something like this, so these two things, something like they must be equal. So that's also one assumption that you will see in the basically your advanced calculus when we will discuss. These are few results that I'm currently borrowing from there. Okay. So now let's look at a few things that we are interested today. That's basically, and today's things are starting from here.
Excuse me, sir.
Yeah, tell me.
Sir, excuse me.
Yeah.
Sir, I have a question.
Yeah.
Sir, why we cannot take grade of a vector?
Grade of a vector A, right? That's what you are saying.
Yes, sir.
Yeah, you see, this operation will not be something like very meaningful. I don't know, because you will see this is a vector quantity, this is a vector quantity, and what exactly this is, you see, you can't say exactly what meaningful quantity you can construct it from, what you can construct out from it right now, right? Because of the fact you just see, now just you break it in the component and something like this, right? And now you see, So you see, even how do you, what we are dealing currently, we are dealing in, for example, let's say we are dealing in your rectangular coordinates, or let's say Cartesian coordinates, right? So the peculiarity of Cartesian coordinate is something like, you can, because you see, you have an operator sitting over here, and this operator will be very much willing to operate on something and perform functions, right? That's what it is meant for. And you see something, the way this operator is operating on, for example, let's look at the first term, x cap del by del x, a x x cap. So what exactly that will be? You see, because of the fact that I cannot say that how my x is, or the basis where I'm just basically writing down my problem, for example, my coordinate system, how I can basically define the orthogonality and non-orthogonality even itself. I mean, for example, they needs not to be orthogonal the way we are looking in the Cartesian systems. वो जरूरी भी नहीं है, लेकिन but for instance, if that is also not to be true, for example, x dot x1 हम हमेशा ले लेते हैं in the Cartesian system, but for example, if we can't take that, for example, we can say x dot x or even x dot y has also a meaningful thing, right? Let's say this is also finite, but even those sort of things are also not generating from here. So I don't know what you can exactly say to this thing. This is, I mean, not a very meaningful thing to basically write in physics. So that's what I would say, I mean, right now.
Okay, sir.
Yeah, so is your question, I mean, yeah.
Sir, what is the meaning of taking grade of a scalar? I mean, what will you do in physical meaning?
Yeah, so that's what we look at it, right? What we said basically, when you take a grad of some functions phi, so I said basically, you say in the previous class, you define something like a function, which is, let's say, a function which is defined by a scalar, let's say, and the scalar will be what? It will be the height from a sea level, isn't it? Let's say this is somewhere 10, this is, let's say, somewhere 20, and let's say this is somewhere 30, right? So I said basically, when we go from, let's say, this is 30 and this is 20, somewhere you go from this to this to this, right? And you see, the way these directions are defined, you see this is a very directional dependent quantity, and the grad phi will be in a direction where the maximum rate of change is happening between these two things, right? So that's the way this grad phi is. It is very much directional quantity, and it has to be operated on this to see the basically the effect of those things, right? So that's why this scalar is given to you. For example, if it turns out to be vector field, right, it will be very cumbersome. The way you see, you are trying to write it down here, right? You cannot define a meaningful thing out of it, because as soon as you make it vector, because it will be very fluctuating quantity on each space time point, and then I don't think so that you can make out any logical conclusion out of it, what exactly this will represent. This you can say this could be something, but exactly in physical sense, I don't think so this will mean much more here right now. But grad operating on a scalar function is truly something which will make sense, at least in physical sense.
Sir, we always have to take the perpendicular distance.
You
Right,
see,
sir?
no, you will notice that this turns out to be done in the direction perpendicular to the basically your defining field. You don't have to take that. You will see that this lies in the direction where the maximum possible change is happening. So which is basically the direction of this, right?
Okay, sir.
Yeah, so all right, let's now define today a few things, and those are something. Yeah, so I'm very interested to let's look at some operations with these operators. Okay, so you see, you have combined this with the scalar function. Let's say, for example, whether you say it's a phi function, which I have took for the case of height from a sea level, or a temperature function, which is defined by its contours, right? So let's say we have defined as a vector field something like this by just operating grad on a scalar function. And then we can also say that we can also write down something like this, but what it will be, right? Whether it will be a vector or scalar or things like that. So you have to answer me that, right? So this is the two possible way that you can play with the grad operator with when you have a scalar function, right? But what about when you have a vector function, right? Let's say I have a vector A and I have a grad, something like this. How can I play with these two things? Like you can see that you can combine something like this, and you can combine something like this, right? There are only two ways that you can, at least in the form of dot products, that you can combine these two things, right? So what these things will be, what this will stand for, and what this will stand for. Can someone comment on that?
Sir, scalar.
This thing will be what? Yeah, sorry.
Scalar quantity.
So this will be a scalar quantity. And what about this thing?
So this will also be a scalar.
No, how could you even say that? I mean, you can't say that, right? Because I said to you, like, these two things will not be equal. This is still an operator. You can't say it's a vector or a scalar or anything. This will still be an operator, right? Because you see, you have not fed anything to operate here, right? You know what way you can feed here things. You can feed, I mean, anything to Dell the way it needs to be operated in a proper fashion. But right now that thing doesn't happen. So it's still an operator. It's not anything scalar or anything. So this quantity that basically I say now del dot A, this what you call basically del A, or basically divergence A, is a very important quantity. Right. So this is basically gives you a scalar, right? The product of two vector functions gives you a scalar quantity, right? And what exactly the physical meaning is, that I would like to explain this in the context of when we basically deal with your integral calculus associated with it. But I just want to see a few more aspects of it. Number one, for example, if you have a vector field, something like, let's say, what I define basically, once you have a temperature contour, and let's say they are maintained and from low to high temperature, and let's say there is a flow of heat that is happening, right? So you will see that heat is always a directional quantity, right? So it not only requires your magnitude to represent it, but it will also a vector arrow on the head, right? The area, basically the amount of heat that is flowing perpendicular to some area. Suppose you take some area over here, you will see that basically the flow of heat basically perpendicular to this area will define basically the flow of your heat, right? So that's the way your heat is defined. So now the point is basically, once I have this H and I have grad and I have combined to produce a scalar, something like this. So now I just want to write, how do you write these two things, right? So what exactly this will be? So that's I want to write. And when I say grad prime, that means I have rotated my axis, let's say angle theta. Okay, so I make my x to x prime and my y to y prime, and I just want to know what exactly now this quantity is. When you know what exactly this quantity is, and what exactly this quantity is, so what exactly this quantity will look like? something like this, right? Right? Do you follow? How can I write this to this?
Yes, sir.
Okay, fine. So yeah, so this is the way that you can combine two vector quantities, especially when you see, I'm just not very much saying the two vector
Hello?
quantity. Yeah.
Sir, are we here operating, operating this del operator on a vector, sir?
Yeah, why not?
Okay.
Yeah, why not? Because you see, because the way this H has been fed to del, right? So you see the way del, it's always coming to its left. So del has to be, del has to operate on this H, and the operation, yeah.
Sir, why you have given that arrow over H?
Because H is a vector field, isn't it? I said it's a basically heat, right? That is happening in a box because of the fact that there is a temperature gradient that has been established in the box.
Something like that.
Mhm.
That means del operator can operate on a vector also, sir.
Why not? It is operating on a vector, right? H is a vector quantity.
Yes.
Yeah, it is not only meant for scalar operations, right? That's what I said. There are various, the way you can play with this operator, right? And the first thing you know that you know how to define a gradient of grad operator, gradient of, let's say, some scalar function. And what that was, something like, let's say, if this is your scalar function, then, and this is your vector function. So you can define grad phi something like this, which is basically a vector function. So the idea was to generate a vector function out of a scalar function through a vector operator. You see my point?
Yes, sir.
And now what you have done, you have combined something like this. You have combined a vector operator, you have combined a vector field. You see, now here, this is a scalar field. I said basically we are talking in terms of field. So you consider this phi is a field. And now you have a vector field H, which is defined on each space and each point of the space-time. Let's not talk about time. A field which is defined on every point of the space, but the peculiarity is that it's not defined by some number, but it has also associated direction, right? For example, if there is a rotating body which is rotating with some frequency omega, and the particle is sitting somewhere here, you will see that the velocity of this particle will always keep on moving, right? So that sort of field will always be a vector field, right? For example, the heat that I talked to you, like when you have a slab which has a temperature difference gradient, like let's say you have a temperature somewhere here, low temperature and 10 degrees Celsius, and somewhere here you have a high temperature 30 degrees Celsius. So since there is a temperature, there's a mismatch of temperature, you will always say that there will be flow of heat from one point to another, and due to that fact you will see that the heat is flowing. And it's basically the heat current that follow to the temperature, perpendicular area. That's the way you define the amount of heat that is flowing out of the body, right? So, but let's not delve into those definition right now. So, but what I said basically considers heat field, which is basically your vector field. And this heat field will be combined with the vector operator, something like this. And what it will produce a scalar. That's very important to know. And that scalar will be something like this. Right? Now, and then I gave you a homework, and I think you do it. Now the idea was, now you transform you see, I measure something somewhere in this system, right? That's what I said. Now I'm just very much willing to know what will happen if I measure something from here. So for example, if I write down something like this function in this frame, and I want to write down this same thing, my vector field is same, only what will happen, let's say I have just defined this with a prime. Now what this quantity will turns out to be, That's what is your homework. Write down the expression for me. Okay, so these few things that I defined to you. Now I just want to write down to you a few more things, and let's say what you can do with grad, this operator, this differential operator, right? You have a vector differential operator, you have a vector field, and you will see I have combined this with a scalar dot product. Now you can also know that when you have two vectors, you can combine them with a vector. When the the product of two vectors can give you a scalar, right? And at the same time, this can give you a vector quantity too, isn't it? So similar way, let's say this was when you have two vectors. But what will happen when you have a vector differential operator? Vector differential operator, and when you have a vector field, what will happen when you want to write down something like this? Okay, so first of all, what this quantity will be? Can someone tell?
Vector quantity.
Yeah,
Vector quantity.
This will be a vector quantity. This will be a vector quantity. And the similar way you write the component of this quantity in, let's say what will be the x component of it? Can you write down the x component of it? What will be the x component? What will be that? Right? Are you following these things?
Yes, sir.
So yeah, similar way you can also write, let's say y component of it, and similar way you can write z component of it, right? So it has a very specific name in physics, del cross H, and it is called a curl of H. Okay, and it is associated with some, of course, you will see that the basically this operation associated with basically when you have a rotating fields, and the basically to study the rotation of those fields, this quantity is useful. But for example, I'm not delving myself right now into those detailed interpretation, but I am just very much willing to concentrate few mathematical aspects of it. So let's summarize a few things. And yeah, let's summarize a few things. And the first thing is, number say, when I say grad of some scalar function, grad t, which I can write down something like this also, this is basically a vector. Okay, and when I say divergence of some, say, let's say a vector function, and the vector function I said basically h, so this is something like del dot h, and this is a scalar, right? And when I say basically curl of h, so basically del cross h, it's basically a vector. Okay, so you will see basically you will always see the implications of these sort of differential operators on a field. For example, when you are going to study in electrodynamics, your Maxwell's equations, right? So Maxwell equation, basically you will encounter that you will always have a field, vector field, electric field, and you will always see that basically this sort of operation associated with this field, this sort of operation associated with this field. Similarly, you will have a magnetic field. Let's say you have a magnetic field, then you can again have an operation with this field, and you can again have a basically cross operation, something like this. What are these things? That you figure it out. Homework. Okay. So
Excuse me, sir.
yeah.
Sir, you have written divergence of H and curl of H. Sir, can we give vector sign over H?
Well, yeah, of course, why not? We can give vector sign over H because H is a vector, right? When you have a vector field, you can always write H. This should be, wherever I'm missing, you just, yeah, nice to remind me. You can always, okay. Okay. Yeah, so is that okay?
Yes, sir.
Okay, fine. So yeah, let's look at a few things that I'm again interested, and those are things something like how do you combine you see, we are till now we are dealing with the basically first derivatives of your field. So I just now want to write the second derivatives. Second derivatives of your particularly, for example, what I mean by it, you will notice in a while. So you know that you can combine this vector operator with some scalar field and produce something like a vector field, right? I want to say that, can you combine this with this, something like this? So this will produce a vector, isn't it? And this is again a vector operator, right? So you will see that basically the dot of these two, what will be exactly the case? So what this will produce, can you guess it? What exactly this will produce? Sorry, you are not very visible.
Scalar, sir.
Yeah, can you again repeat?
Scalar,
Yeah.
scalar.
Yeah, of course it will be something a scalar, but we will see shortly. Yeah, sorry. Yeah, what you said? You can write in chat box too, for example, if you're not able to speak properly.
Sir, it will be del square T upon del X square plus del square T upon Y del Y square plus del square T upon del Z square.
Yeah, that will be very much like it. So we will see basically, you see, what I mean is basically you can write this thing. So everyone is following something like this, and you can write down something like this, right? So this is perfectly okay to write because these two are operator and this is just a scalar, and which is sitting on the extreme left. So you can keep it in that fashion, and you can couple these two vector operators, something like this. And you know that basically del is what? It will has component something like del X, and it will have something component del Y, and it will have something component del Z. And similar way, this will be also having del X, del Y, and del Z. Okay. So you will see that when, I mean, this is shorthand to write del Xi cap and Y cap on. And you see the only, since there's a dot product associated with this, cross term won't be appearing. So del X, I will say something like del by del X2, and then basically del by del Y2 and del by del Z2. And it will operate on some scalar field. So this operator is especially very unique in physics. You will notice it appears in many places. You will also notice this has a specific name. We define it. Yeah. Tell me.
Can we means
Sorry.
sir, will it be meaningful if I say grade of a vector, or only scalar is meaningful?
Grade of a
Vector.
I don't think so that grade of a vector field is going to be very meaningful thing, isn't it? Because of the fact that I said to you, right? For example, you have a vector field operator, something like that, and you want a grad of this function, right? So what exactly this will be, right?
Yes, sir.
So I don't think so this could be a very meaningful quantity for you to speak on, right? For example, it will have something like this plus something like this. The way I try to explain now, if I break something like this, now you see what exactly I can make out from it, right? Now, if I just want to write it down, you see, I have an operator sitting here, but since you see, this is a vector operator, right? And this is a vector again itself, right? So you see how two vectors get combined. If I have this vector and I have this vector, how you can combine two vectors? What are the operations that are defined? Either you can combine them something like this, or you can combine something like this, right?
Yes, sir.
Right. So the similar way, when you have two vectors, something like one may be a differential operator. So the differential operator will, of course, have a true aspects, like it has to be fed at something. But for example, when you have given a vector, it will be very meaningful to define the operation. The operation will be defining something like this. You see my point?
Excuse me, sir.
Yeah.
Sir, I think that term will be del square by del x square plus del square by del y square, like this.
That before t.
Yeah, yes, sir.
Yeah, of course. This is a second derivative, right? Because you see, this del x and del dot del x, they will combine and will produce del x square, right? So that square means del x, I mean basically something like del by del x, right? So this will be twice of that. Fine. Is that okay?
Yes, sir.
I see. Okay, so what I was willing to know basically that the number one that I defined, that how do you define a second derivative, something like this, and you have noticed that this is turns out to be something like this, and the quantity this, I have said, this is known in the physics something like a name called Laplacian, right? That has its own significance, but you will notice shortly where it appears. So now this grad square be operating on a vector field too? For example, if I want to write something like this, is this meaningful?
I think no, sir.
Okay. What other things?
No, sir.
No, sir. What anyone else is there?
No, sir.
So why no? I mean, this is a vector field. This is a scalar operator. Why can't you do that? I mean, who is stopping you to do that? Why can't you write something like this? What is the reason by saying no? Who is stopping you to write something like this? This will be, of course, a vector field. But is this a vector field? Can you prove that to me? Or on what logic you are saying this is no? Okay. Homework. Take this as a homework. Okay. So is this true? And if this is a vector, then why this is so? Okay, fine. So let's look at one thing more. For example, I said you can, sorry, wherever I forget, I mean, you can remind me. For example, whenever I write del, it should come with basically a vector sign, right? So you know how to combine, right? You write a gradient, something like this, right? And then this is again a vector field, isn't it? And you know that you can combine a vector field to a vector field by a curl operation too, isn't it? Right? So what will this quantity be? Can someone comment on that?
0, sir.
Why that is so?
Sir, curl of gradient is 0.
Why? Who says, I mean, why it should be 0? Curl of gradient 0. Why that is so?
Sir, I cross I is 0, and I mean, sir, x cross x is 0, y cross y is 0. So in both del cross del, it contains x, y, z. I think that's why, sir.
Yeah, of course. I mean, the best way will be to look at basically you see, basically the point is you want to just calculate it something like the way you write the component. Let's say, for example, I want to write it the z component of it, whole thing. What will be the z component of this whole thing? Something like this is y, right? Minus, what will be that? Whenever I write, and when since you see basically, so now what this thing will be? So just these are just components.
Yeah, it's going to be helpful, Rohit, if we can write in a determinant form, then it will be very visible.
Yeah,
that
of course.
What could be the component and why the physicality is going to be there.
Yeah, of course, you can always represent this in a basically determinant form. But I think that you all know from your class, basically you can write down. I think it's a very trivial exercise. You can take this as a homework if you want to prove in a determinant form. But you can take a look from here, right? What will be exactly this thing? Del 2t by del x del y minus del 2t by del y del x, right? So you see, while we writing a perfect differential, we have took some assumptions, right? And what are those assumptions? That for this to be perfect differential, the second derivative should independent of their orders, right? That's what it means. This is del y. So that means these things should be something like del y del x. So that's the basic definition for a function to be perfectly differential. And that gives you the basically makes that quantity this to be something like 0. So let's also construct a few more second derivatives of field. So those could be helpful in physics. For example, let me write down how about, for example, if you have I was just talking about scalar field, right? Now suppose if you have a vector field H, right? And you have a vector operator, something like this, right? How do you combine these two things, right? You know that basically you can combine this as a dot product and as a cross product. For example, if you have combined this as a dot product, right? So this dot product, what this dot product will exactly represent? This will be a scalar quantity. And if you operate this on something like this, what exactly this will be?
A vector quantity.
A vector quantity, right? So that's also, you can do that. I mean, you can also combine these two things, something like this. But again, you can also combine something like grad and h in a cross fashion and take something like this. This will be again a vector quantity, right? And when you have a vector quantity, you can again form a scalar quantity, something like this. When you have a vector quantity, you can again form a vector quantity, something like this, right? So this is again a vector quantity. You multiply with another vector and form again a vector quantity, right? So the idea is basically, I mean, a few things could be even more helpful. For example, this thing, if you want to look at last thing, for example, I just take this thing. So how do you write this thing? what exactly this will be simplified to. So for example, if I say to you, you can take use of this thing and simplify this thing. So what will be the answer? How do you write this thing? What else? Is this okay?
Yes, sir.
Yes, sir.
So now tell me what exactly this will look like. Right, so C will be replaced by which? H, right? So you can properly write it. So yeah, so let's write it with something like H and H. Okay. Okay, so this way you can simplify, but can you look at these two equations where I'm just highlighting 1 and 2? Let's say this, if this is my equation 1 and this is my equation 2. I mean, is this the right way to write it down? Can someone comment on that?
Sir, can you please repeat the question?
Yeah, I said, I mean, is everything is okay with equation 2 and 1?
Yes, sir.
Everything is okay. What about others? What they feel?
So we can write del square.
This
Del, we can replace with del square.
del square, fine. So this will be something like this. So what about now? Is this and these two things are okay? Equation 1 and 2. This is equation 1. This is equation 2. Do you notice anything here? For example, let's look at equation 1. So what will be A cross B cross C will be? What will be B cross C? Will this be a vector quantity or a scalar quantity?
Vector quantity.
B cross C will be a vector. And when you multiply a vector quantity with a vector quantity in a cross product, what will that amount to?
Vector quantity.
A vector quantity. What about the right hand side?
A vector quantity.
A vector quantity. So everyone follows that the right hand side is a vector quantity. I'm just going to take another slide. So did you follow that? That when I write A cross B cross C, something like B, right? So this equation 1. So when I said to you basically that when we define vector, right, we say that the vectors are basically in a very normal sense have magnitude and directions, but then we also elaborated what is the basic definitions, I mean, of vector is like they follow some transformation laws associated with the translational and rotational invariance, right? And we concluded a few important things. And what was those things? That useful physical laws do not depend upon the orientation of coordinate systems, right? Isn't it? That's your first law. And what is that? I would like to state it here. Useful physical laws maybe you can write translational first because we have looked translational first. Translational, I mean, translation of coordinate system, not translational, but you can say orientation and translation of coordinate system. So, and this led to be very important implication. And what is that? What that means to, I mean, that should be mean to be something like they should therefore be written in the form, which is basically, I mean, you can write down an equation or a law in a form which is basically in either side maybe a vector quantity or maybe a scalar quantity, that's all. But that should be the case. For example, if your right hand side is a vector, your left hand side turns out to be vector. When I just said to you, and I just write down before you that something like the last one, I mean the slide, something this, that you can combine a vector field with something like this. And you have said by equation 1, you try to write down something like del dot h minus h grad square. You notice a very important aspect, right? This is still an operator equation, right? Here you see the operator is still unsatisfied sitting here, right? This is an unsatisfied operator sitting here. And of course, this could be a vector in the extreme left hand side sitting here. This could be a vector, but this is still a Hungary operator sitting here with a grad square, right? Because you know that grad square is again an operator, right? Which has 3 components, del 2, del x2, del 2, del y2, and on so on, right? So this is still in Hungary operator. So what is wrong with this? Can anyone point out that?
Sir, del square should be in front first, so that it will operate on H.
Yeah, that's a very nice observation, Zumi. Del square should be right, so that, I mean, equation could make a sense. So, and could even someone try to elaborate a bit more? So I think with that short note, I will again put this as a homework. Find out why this is the case and what we have done wrong, right? So with this, I mean, we have more or less formed all the second derivative that we could make out of all our first ones. So like we can formulate a grad t, we can formulate a divergence h or curl h, and with those operations we could always, I mean, maybe a couple of more we can make out. Maybe that would be coming in the next class. So with these 2 things, I mean, I would just write to stop it here because I think I have already passed my time limits here. So if anyone has any questions, we can take a few 1-2 questions. Otherwise, I'm just going to stop it here. Okay. If anyone, I think if no one is asking, I'm just going to conclude it here. So thank you for, I think, joining for today's class, and maybe we then meet next time.
Thank you, sir.
Thank you, sir.
Okay, fine.